In the last segment, we saw how inductive reactance limits current and how inductance causes current and voltage to be out of phase. We're going to be talking about phase relationships again in this segment. We'll see how capacitance also causes current and voltage to be out of phase. But the effects are not the same as we saw with inductance. In fact, the effects of capacitance on voltage and current are such that capacitance is often used in a circuit to counter the effect of inductance. But I'm getting ahead of myself. Let's begin with capacitance. Capacitance is the physical property of all AC circuits that opposes a change in voltage. Because capacitance opposes a change in voltage, it has some effects that you should be aware of. For example, the capacitance in high voltage motors and distribution cables causes these motors and cables to store up energy. That stored up energy doesn't go away every time you turn off the power. So if you go to work on a motor that has had its power turned off, you still might get a shock from the stored energy unless you discharge that energy first. This energy storing business has some advantages too. As I said earlier, one of the uses of capacitance is to counter the effects of inductance. When the inductance in a circuit would limit current more than a desirable amount, additional capacitance can be added to that circuit to bring current flow up to the level that's needed. The devices that are added to electrical circuits to increase their capacitance are called capacitors. A capacitor is a device that stores energy. A typical capacitor is made up of two plates separated by an insulator. The insulator is called a dielectric. The dielectric keeps electrons from flowing from one plate of the capacitor to the other. Before a capacitor can store energy, it has to have some energy supplied to it. That's called charging the capacitor. And this very simply is how it's done. When a capacitor is connected to a power source, electrons flow onto one of the capacitor plates. They stay on that plate because the dielectric keeps them from getting to the other plate. The first plate thus has an excess of electrons, so it has a negative charge. Because like charges repel each other, the negative charge on the first plate forces electrons away from the second plate. The second plate thus becomes positive. Electrons from the positive plate flow back to the power source. The flow of electrons from the power source to the negatively charged plate of the capacitor and from the positively charged plate of the capacitor back to the power source continues until the peak voltage is reached. At this point, the capacitor is charged, and the positive plate has lost the same number of electrons that the negative plate has gained. It is important not to overcharge a capacitor, because overcharging can damage the dielectric. What happens in a capacitor is really quite simple, but it can be confusing. Perhaps we can get a clearer picture from this diagram of a mechanical system. This cylinder has a flexible rubber membrane in the middle of it. The rubber membrane blocks off the cylinder the same way that the dielectric blocks off a capacitor. Now, the cylinder is filled on both sides with balls. If an attempt is made to force an additional ball into the left-hand side, the rubber membrane will stretch, and a ball will be forced out of the right-hand side. An observer who couldn't see inside the tube might think that the ball that was put in had traveled all the way through the tube. This is similar to what happens to electrons in a capacitor when the capacitor is being charged. For each ball inserted into the left-hand side of the tube, one ball will leave the right-hand side, but no ball passes all the way through the tube. The number of balls in the tube stays the same, it's just their distribution that's different. If someone kept on trying to force more and more balls into the tube, the process would become more and more difficult because the rubber membrane has a tendency to spring back to its original position. In fact, if too many balls were forced into the tube, the membrane would rupture. After the membrane ruptured, any number of balls could be put in, and every one of them would go all the way through the tube. A similar effect occurs in a capacitor when the voltage that's supplied to it is too high. If an excessive amount of voltage is supplied to a capacitor, the dielectric material will break down. When that happens, current is able to flow through the capacitor. In most cases, current flowing through a capacitor will destroy it. Okay then, that's how a capacitor is charged, and that's what happens when it gets too much voltage. Now, let's see what happens in a capacitor during a complete AC cycle. This circuit contains an AC power source, a capacitor, and a switch. As soon as the switch is closed, electrons start to flow. Electrons accumulate on one plate of the capacitor, and electrons depart from the other plate. That's the charging action that we saw earlier. As the capacitor is being charged, a difference in potential develops across it. Each electron that's added to the first plate makes that plate more negative, while each electron that leaves the other plate makes that plate more positive. A difference in potential is voltage. So what happens is that a voltage is building up across the capacitor. And the polarity of that voltage is such that it opposes the source voltage. As the capacitor continues to be charged, the voltage across the capacitor increases until it is equal in amount to the source voltage. At this point, the capacitor is fully charged. Because the source voltage and the voltage across the capacitor are equal in amount, but opposite in polarity, they have the effect of canceling each other out, and current stops flowing. What we've just seen is the first quarter of the AC cycle. Let's go through it again, this time with the aid of some sine waves. We'll be using two sine waves, one for the source voltage, one for the current. And we're assuming that this is a purely capacitive circuit. There's no resistance or inductance to affect what happens. As the source voltage starts to rise from 0 to its maximum positive value, current flow from the source to the capacitor is at its maximum amount. As the source voltage rises, the capacitor is being charged. When the capacitor is fully charged, the source voltage is at its peak positive value, but current is at 0. This is because the opposing voltage that is built up across the capacitor during charging effectively cancels out the source voltage. So there's no voltage to cause current to flow. When the source voltage passes its positive peak, the capacitor starts to discharge. Discharging is the reverse of charging. Electrons flow onto the positively charged plate, and electrons leave the negatively charged plate. Current flows in the negative direction. When the source voltage reaches 0, current flow is maximum in the negative direction. Similar relationships are evident for the negative portion of the source voltage sine wave. As the source voltage rises from 0 to its maximum negative value, the capacitor charges. When the source voltage reaches its maximum negative value, the opposing voltage is at its maximum positive value. The capacitor is completely charged in the opposite direction, and current flow is 0. As the source voltage passes its negative peak, the capacitor again starts to discharge. When the source voltage reaches 0 again, the cycle is complete. Before we leave the subject of capacitance, I want to mention 2 points that we'll be coming back to later on when we relate the effects of capacitance to the effects of inductance. First, look again at the sine waves for source voltage and current in a capacitive circuit. As you can see, capacitance causes voltage and current to be out of phase. In a capacitive circuit, changes in current always take place ahead of changes in voltage, because capacitance opposes a change in voltage. In a capacitive circuit, then, current leads voltage. The second thing I want to mention is capacitive reactance. Capacitive reactance and capacitance are related in exactly the same way that inductive reactance and inductance are related. Capacitive reactance is the measure of the opposition to current flow caused by capacitance. As the opposing voltage builds up, current decreases. So it can be said that the opposing voltage limits current. As we said earlier, measurements of the amount that current is limited are always given in ohms. So the units of capacitive reactance are ohms. We're going to be talking a lot more about capacitive reactance and inductive reactance and about voltage and current phase relationships in the next segment, which covers AC power. Now, why don't you read through section 3 in your text first? Make sure you understand what we've said about capacitance, capacitive reactance, and capacitors. If there's anything you're not sure about, ask your instructor.